So now that you've finished section 6.3 and all of the videos that the author has, I really like those videos and I like how he's explaining everything. But if we were face to face, I would want to add in some tidbits or tips, some comments, and also get you to put some of these items, or at least find these items, on your formula sheet. If you haven't already, go ahead and hit pause on this video and go print the 2 pages of the formula sheet, which are in document sharing in My Lab Math. So the first thing I would like to point out is when we have, and you can't see me pointing at the top, but at the top I'm pointing at range, and I'll go ahead and just point at the bottom of this page, because at the bottom of this page there is a chart. And the chart summarizes domain and range for all 6 of our trig functions. I really like how the author explained this using the unit circle. I really encourage you to not really memorize this chart, but just be really familiar with, help this chart to make a whole lot of sense about what is going on with these trig identities and the domain and range of all of the functions. And so I'd like to show you a couple of things, because I would have shown you this in class had we been face to face. But looking here, I would like to talk a little bit about domain and range. And again, I'm just hitting highlights. You've already gotten the meat of the matter, but looking at domain, remember that domain is everything X can be, and range is everything Y can be. And I don't want to freak you out, but I do want to go ahead and look at the graph of sine. We will eventually get there, but just to keep talking about what is going to be the domain of sine and what's going to be the range of sine, you've already been looking down here and we've already talked about it, and you've seen it in the video and probably read it in the book. But if you look at the sine graph, which you don't know, you don't need to know right now, I just want to bring it in and let you see something, that when we do go to graph sine, it's going to look something like this. And what I want to point out is when we're talking about domain and what can all of the x's be, notice, and let me change pins, notice that if we're talking about the x, is there ever a place that this is going to stop going to the right? Is there ever a place this is going to stop going to the left? And no. The domain for the sine function is going to end up being infinite, all the way to the left and all the way to the right. And if you look here, you've already seen and discovered that the domain of sine is all real numbers. It goes forever to the left and forever to the right. I just wanted you to see that and add into what you've already documented and written and thought about. And then I want to talk about the range for the sine function. And the range is everything y can be. And you'll notice y only goes up to 1 and y only goes down to -1, and it actually can go down to -1 and touch it, and it can actually go up to 1 and touch it. And right here, when you were looking at the range of sine, it is -1 to 1 inclusive. It can include the negative and positive 1. I like the picture of the graph. My brain defers to that often when thinking domain and range, and later when we get to what we're going to call inverses, where we're going to block this, the graph comes in handy. So I want to also show you the cosine graph. The cosine graph is very similar, but it's shifted. We've talked about periodicity. We've talked about a cycle. We've talked about the recurring of all of these terminal angles. A lot of stuff is going on. And so later, not right now, we're going to look at the cosine graph. And on sine, we actually have what I will call start at 0 and go up and then down. When we go to graph cosine, we'll start at 1 and then go down and then up. And you'll notice it looks very familiar, and I got that way too far out. Very familiar to the sine graph, and we will talk more about that. But again, I want you to notice we're talking about domain. Domain is everything x can be. And again, you'll notice this graph is not going to stop going to the right, and the graph is not going to stop going to the left And as you saw in the tables, cosine's domain, well, it's everything. All real numbers, all the rationals and all the irrationals. And then the same thing happens here if we're looking at range on how high and how low can our cosine graph go. And right here, you will notice it's all real numbers from -1 to 1, and it is inclusive. And the only other graph I want to show you, I want to talk about tangent. And tangent is just in a league of its own. And I know that we've talked about and looked at that tangent is going to be undefined wherever x is 0, where x is 0. And so if you were talking about the quadrantals and you're looking around, x is going to be 0 at pi over 2 and at 3 pi over 2. And in fact, we can just say it's going to happen on every pi over 2, every odd multiple of pi over 2. Like at 1 pi over 2, 3 pi over 2. And that would bring us back around here, and we could call it 5 pi over 2. And back down here will be 7 pi over 2. You get the idea on all of the odd multiples, and we just get a little lazy and call it k, or go ahead and say it's the odd multiples, but k times pi over 2 as long as k is odd, which includes 1, it includes -1, it includes 3. Pi over 2 is what I'm going to hinge on. So when I look right here at pi over 2 and negative pi over 2, because that's a 1 pi over 2, which is an odd integer, and -1 is an odd integer, I cannot define tangent there, and it's going to be asymptotic. And we're going to see a graph of tangent where it's going to come up and go up like that, and I've crossed over the line and I shouldn't have touched it. It's going to come from down infinity, and it's going to head off to infinity. But I want you to notice, what can the x's be? Well, the x's can be a lot between here and here, but they can't be a pi over 2. And then you're going to find they can be a lot, because we're going to repeat this process. We're going to do another one of these. It can be a lot of values for x between pi over 2 and 3 pi over 2. See over here? But it cannot land on 3 pi over 2. And so what ended up happening on the x is it's going to be all real numbers except the odd integer multiples of pi over 2. I just wanted to show that to you graphically and talk about it a little bit more. But what about range? What about y and what it can be? Well, if you look, does it look like it's ever going to stop going down? No. Is it ever going to stop going up? No. So it's infinity. Y's can go all the way down to -infinity, and they can go all the way up to positive infinity. Hence, tangent's range is going to be all real numbers, which can be -infinity to infinity. I wanted to look at page 395 and go to the very, very bottom. At the very, very bottom, I wanted to point out this paragraph at the bottom of 395 talking about period. I cannot stress enough that you start to get in your brain that sine, cosecant, cosine, and secant will all have a period of 2 pi. All. But tangent and cotangent have a period of just pi. And if you don't start getting that in your brain now, it's going to wreak havoc on some of your future trig concepts. Really, really, really think on this in either the drawings or looking at the unit circle. But really take a moment to pause and let it sink in about the period being 2 pi or pi based on which of the functions, which of the identities you were talking about. So I wanted to talk about domain and range. I wanted to show you that at the bottom of 395. I wanted to talk about k and how it's it can be ones, zeros, and it just depends on how we define it. You may or may not have seen that before. And then I wanted to look down here at page 397, and you start to see identities. And so something you may want to do, if we were in class, I would say, hey, pull out your formula page and start looking for these identities. And when you see this reciprocal identities, It may or may not be labeled, but if you look up here at the top, you might highlight them, put a little star or mark beside them like, hey, we've talked about those. It's really good to see it in multiple forms. Also, you have the reciprocal identities. Well, what it did here, and notice it's got the little arrow, when you multiply these, when you multiply a sine times the cosecant, which is the reciprocal, then it's going to turn out to be 1. It's just another identity. Down here, it says quotient, but I wrote in ratio, because if you look here on your chart, we have the same thing, and I would memorize what I like to think of on tangent, is remember how we saw it's y over r? Well, sine relates to the y and cosine to the r, and then when you do the reciprocal, this one was x over y, which that relates to the cosine, and that relates to the y. I also wanted to tell you, let's see, that was the one on page 397. So I also want to talk to you about what's on page, wait, I think there's more over here, there are. On page 398, you see the trig identities. Well, that's what we're studying, is trig. But these are the Pythagorean identities. I'd even note those on here that I have looked at them. But one additional thing you might note on there is not only do you have to know these identities, and by the way, the first test, you're not using the formula sheet. So these have to be memorized, and there aren't a lot, and a lot of them are just common sense. But you need to memorize these for your first and second tests, and then the third test, third test and the final, you'll be able to use your formula card. But the other thing you need to note on this is not only do I need to memorize sine squared plus cosine squared is 1, I need to know that if I wanted to rearrange this, like move over my cosine squared, and it would be gone from right here, I also need to know that sine squared theta is the same as 1 minus cosine squared. I need to be comfortable with rearranging my Pythagorean identities. And so the first one's probably pretty easy to memorize. These two aren't bad, but notice which ones are going together, not the tangents and the cotangents. It's the tangent and the secant. And they have something in common, and I'll let you think on what that might be. Moving on. Whenever we look onto page 402, on 402, I wanted you to see the even-odd properties. And then I want you to look on your formula sheet, and down at the very bottom, there they are. And so this is just a great, concise page that you can take with you as you go on to pre-cal and cal, and maybe even keep whatever major you go into, keep this with you as a quick reference. As professors let you use it, that would be good. And I wanted to talk also about, we got everything? Did all of those? Okay, so let me move on to, oh, I did, on the other side, on the unit circle side. On the unit circle side, there are the graphs of cosine and sine, and the tangent graph, where it's blocked between negative pi over 2 and pi over 2. I did want to show you those. We've already looked at the unit circle, and I do want to work one problem. I want to go to example 3. And on example 3, that's 1. So looking at example 3, I wanted to show you what I like and what I do a lot when I'm, oh, you can't see that, when I am working these problems. I like you seeing multiple ways to work our trig examples, our trig concepts. The thing is, it can get confusing. So you've got to be real clear on where you are, which one you're doing, and in this case, when it's asking us that they gave us some theta, and they want us to find the exact values for the other 4, so secant, cosecant, tangent, and cotangent, I really like drawing the triangles. It helps my brain to get oriented, and if we're just going to have any old theta, where the sine ends up being positive and the cosine's positive, that means the x and the y are positive, then that lands us in quadrant 1. And when I go look at sine, I know it's in 2 parts. I know it's a y over an r. And so that tells me square root of 5 is my y value, and 5 is my hypotenuse value. It's pretty straightforward. It is what it is. So let me check this one out. Cosine. Cosine is x over y, x over r. And so that means my x value will be 2 square root of 5, and my r is, well, 5. And I already knew that. So it all matches up. I have my first 2 trig identities. I now need to go find the rest. So I even, well, all semester tell you to use your given. And so I'm going to go back up here to use my given. And as I say that, I'm even going to play around with the drawing. But using my given, when I want to go look at what is cosecant, cosecant's going to be the reciprocal of sine. And with it being the reciprocal of sine, I'm just going to take sine, do its reciprocal, and then I need to rationalize my denominator. And so I get 5 square root of 5 over 5. Wow. 5 square root of 5 over 5. And I end up with just a square root of 5. I will bring back in SOHCAHTOA. And when we're dealing with sine, we know its reciprocal is cosecant. And we can even play, double check, and think, not during the test, but as you're learning. You will see me in the notes ask you to do an example without looking at your notes. And so as you're doing this course, you've got to understand when you're learning and when you're double checking, and then when you got to do this all by yourself. I do think the more you look at information, the more it starts to gel in your mind. But if I want to find cosecant, I know it relates to sine, but sine is opposite over hypotenuse. So cosecant will be hypotenuse over opposite, hypotenuse over opposite, hypotenuse over opposite. So it's one of those things that when you finish your test, you can go back and check it through the back door. There are multiple ways to do this. We're not done though. So let's look at secant theta. Secant, I can go up here and do my hypotenuse over adjacent. I could do hypotenuse over adjacent. Well, I'm going to defer and go back to the given. And the given was to take 5 over 2 square root of 5. I've got to rationalize my denominator. And when I do, and you can't see all of that, I get 5 square root of 5 over 2 times, oops, not 10, 2 times 5. My 5's become a 1, and so I get square root of 5 over 2. And I usually like to double check and see, am I matching the book? And so cosecant, they got square root of 5. We matched. I probably should have rewritten that, but I was out of space. Got lazy. And then my secant is the square root of 5 over 2. And so when they look here at, they've already calculated tangent, they've already calculated cotangent, and this is about the time I go pretty lazy. And so I'm going to go ahead and look at tangent theta here. And when I go to look at tangent theta, tangent is opposite over adjacent. If I've done all of these and I'm feeling confident that my numbers are correct, I'll just go opposite over adjacent. And I'll remove the square root of 5's because they became 1, and we're at 1/2. So I look for lazy things to do as long as I'm still being accurate. And so cotangent is the reciprocal of tangent. And so instead of 1 over 2, it would be 2. I will double check with them in the book. And their tangent, they got a 1/2, we did 2. And then their cotangent, they got 2, and so did we. On page 399, there is a group of fundamental identities. These are the ones that you need to have memorized for test 1. And a lot of them you're looking at going, I've already got it. I'm a little shaky on these two. Great. Put them on a flashcard, memorize those, and you're good to go. So just looking at my notes, I think I've mentioned everything I wanted to mention in this conclusion and kind of summing up everything that you've seen. Oh, and then I see one more thing. Let me just make one comment that I always like to stress, and it's back here at our odds and evens. My brain needs to memorize, but my brain needs simple and something easy to remember. And so when I look at all of these, I'm like, oh my gosh, I can't memorize all of these. I mean, I could, but maybe there's an easier way. And I think the easier way is every time we go to talk about even odds, I would ask you maybe the 2 oddballs or the 2 even ones. So I guess that wouldn't make them oddballs. But looking at this, everybody, when we put in the sign of the negative theta, it's going to turn out to be the negative sine or the negative cosecant or the negative tangent or the negative. But the ones that don't, sometimes it's easier to memorize who doesn't. And so when I put in cosine of a negative theta, wow, it works out it's just the cosine theta. And the same thing with secant, because these are related, they're reciprocals. And so all I'm saying right now is that you might want to consider when you're memorizing even odds, is just to memorize the ones that turn out perfect, the ones that turn out just as they are, and that might help you. The last thing I will say is my little sticky note down here. Whenever we go later in this semester and we're talking about doing some symmetry checks, and you might remember this from college algebra, when we go to do symmetry checks, this negative theta is what we're going to plug in, and that's going to be our test. And when we plug it in, we will find out that if it becomes exactly the opposite, like we plug it into sine and it becomes exactly the opposite, exactly the opposite, exactly the opposite, it is going to be odd, and it's going to be what we call opposite, but there's a little bit more where we get to declare that it has origin symmetry. And again, with me memorizing, I've got to look for things that make it concise. So when it turns out odd, we will call it opposite. That's how we know it's odd. And it will possess origin symmetry. But these other two turn out to be the same. I started with cosine, I end with cosine. I started with secant, I end with secant. And when it's turning out to be the same, then we're going to call that an even function. And every time we will also say it has y-axis symmetry. This is a little bit more jagged for me to memorize, but all of these O's, I got it. Odd is opposite, and I'll call it origin. Well, what's the other one? Well, it's the other stuff. It's not odd, but it's even. It's not opposite, it's the same. This one's a little dicey, and I just have to know that origin or y-axis, and we won't have x-axis. So I'm done with just kind of summing up 6.3. Keep up the hard work.